Hi everyone, today we will take a look to a super useful technique that is called secret sharing and allows a party to split some information into pieces that are called shares and distribute them among a set of parties, and also define a rule that specifies which parties are required to collaborate in order to reconstruct the secret. This technique can be used, for example, to do not store a secret information that may be valuable in just one place, but distribute it among different servers. Or also it can be used as a building block for secure multi-party computation. So here we see the idea of secret sharing in a more formal way. We have a secret S and we want to split this secret into shares S1 to Sk among a set of parties P1 to Pn, such that the secret S can be reconstructed through the cooperation of chosen sets of parties. Otherwise, no information is obtainable. So what does it mean? It means that if a set of parties that is not authorized to reconstruct the secret tries to reconstruct it, it obtains no information at all. And if we have n parties, in order to reconstruct the secret, we may require all the n parties, and we call this scheme n out of n secret sharing, or any subset of parties of size t of the n parties, and we call this case threshold secret sharing. And finally, the most general case is the case in which we authorize arbitrary sets of parties to reconstruct the secret. And in this case, we talk about general asset structure secret sharing. Let's take a look now to a few definitions, and then we will go through examples. So we call a qualified set a set of parties that is authorized to reconstruct the secret, and we call an unqualified set a set of parties that is not allowed to reconstruct the secret. Then we call an asset structure the set of all the qualified sets, and a secrecy structure the set of all the unqualified sets. It is useful to note that every superset of a qualified set is also a qualified set. It means basically that we have, for example, two parties P1 and P2 that can reconstruct the secret. Then each set that contains these two parties is also authorized to reconstruct the secret. And because of this, we can define an asset structure in terms of minimal qualified sets. And in a similar way, every subset of an unqualified set is an unqualified set, so we can define a secrecy structure in terms of maximal unqualified sets. And now let's take a look to an example of how we could try to do secret sharing in a wrong way. So suppose we want to share a secret, that is the string secret actually, among three parties. Then we can split the secret in this way. We consider as the first share the first two letters, as a second share the third and the fourth letter, and so on. And then we send S1 to party 1, S2 to party 2, and S3 to party 3. The problem of this approach is that while we require all the three parties in order to reconstruct the secret, each share says something about what is our secret. While according to our definition, we want that a number of share that is smaller than 3 should tell nothing about the secret. So how can we do secret sharing, in general n out of n secret sharing, in a secure way? Suppose that our secret can be represented as an element of the additive group of integers modulo q. Then the dealer, that is the party who wants to share the secret, has to proceed in that way. She has to sample n-1 uniformly random shares from the group we are considering, and then the last share is computed in that way. So the secret minus the sum of the previously computed shares modulo q. In that way, we have that the sum of all the shares give the secret, but if we don't have all the shares and we try to sum them, what we obtain is something that is completely random. And then, as a last step, the dealer has to send Si to Pi. So in that way, the secret S can be reconstructed only if all the shares are known, and this requires all the n parties to cooperate according to the way we distributed these shares. And now let's see how it works with a numerical example in the case of 4 out of 4 secret sharing. So here we have 4 parties, and still the secret S belongs to ZQ. Then we can consider, for example, S equal to 42 and Q equal to 256. Then the dealer has to split the secret 42 into 4 shares, for example, S1 equal to 34, S2 equal to 75, and so on. And finally, S4, that is the last share, is computed in that way. So 42 minus the sum of the shares computed in the previous step. And then S1 is sent to party 1, S2 is sent to party 2, and so on. So from this table we can see the way the shares are distributed, and since all the shares are required to reconstruct the secret, all the parties from P1 to P4 are required to cooperate. And we achieved what we want. Now, how can we generalize this to the case of T out of N and general asset structure secret sharing? So let's suppose again that the secret is an element of the group ZQ. Then the dealer has to proceed in that way. All the possible maximal qualified sets have to be defined, and then for every maximal qualified set Ti, we have to compute Ti hat as the set difference between the set of parties P and Ti. Then we will obtain a number of sets equal to k, and we split the secret S into k shares as we have seen before, and again send the share Si to all the parties belonging to the set Ti hat. This may sound a bit complex, but we will take a look to an example very soon. Again, all the k shares are required in order to reconstruct the secret, and the way we distributed the shares guarantees that each qualified set that have been defined implicitly by defining the maximal unqualified sets knows all the shares that are required to reconstruct the secret. Here is an example with 4 parties and T equal to 2. That means basically that any subset of sites 2 of the 4 parties is authorized to reconstruct the secret. So as before, we have P equal to the set of parties, S belonging to ZQ, and here we define the maximal unqualified set. So since we said that we need at least 2 parties to reconstruct the secret, we have here that each set of 1 party only, of course, cannot reconstruct the secret because we need at least 2. And then this is T1, this is T2, and this is T3, and so on. Next, we have to compute T1 hat, T2 hat, and so on by computing the difference between the set of parties P and the set T1 and so on. So let's try to compute together the first case. P is the set of parties P1, P2, P3, P4, and T1 is the set containing only P1. So the difference of these two sets is P2, P3, P4. Then the others can be computed in a similar way, and we have obtained 4 sets. So the dealer has to split the secret into 4 shares, as we have seen before, and then send Si to all the parties Pj belonging to Ti at. So it means that basically S1 is sent to all the parties belonging to T1 at, so P2, P3, P4. In this table we can see exactly how the shares are distributed to the parties. So S1 goes to P2, P3, P4, S2 goes to P1, P3, P4, and so on. And from this table, it is very easy to see that any two parties, for example, P1 and P2, if they cooperate, they have all the shares. For example, P2 as S1, P1 as S2, and then they both have S3 and S4. And this holds for any couple of parties. Now let's look to the most general case, that is the general access structure secret sharing. In this case, we can suppose that we still have 4 parties, S belongs to ZQ, and we want, for example, that the only ways in which the secret can be reconstructed is if P1, P2, and P3 cooperate, or any of them cooperate with P4. So what does it mean? That we have the following secrecy structure. So P1 and P2 only cannot reconstruct their secret, P1 and P3 cannot reconstruct their secret, P2 and P3 cannot reconstruct the secret, and P4 only cannot reconstruct the secret. And that's all. And in this case again, T1 is equal to the set containing P1 and P2, T2 is equal to the set containing P1 and P3, and so on. So we can compute T1 at, T2 at, T3 at, and so on, as we have seen before, by computing the differences between the set of parties P and T1, T2, and so on. And again, we obtain 4 sets. So the secret is split into 4 shares that are distributed according to the same rule we have seen in the previous case. So Si goes to all the parties Pj belonging to Ti at. And here we can see again a table that summarizes how the shares are distributed to the parties. So in this case, we can see that P1, P2, and P3, if they cooperate, they have all the shares. P3 as S1, P2 as S2, and P1 as S3, and all of them have S4. And also, if any of these parties cooperate with P4, they still have all the shares. So if you want to play with this type of secret sharing, that is one of the possible types of secret sharing, you can download the script I've published on GitHub that allows you to try all these different techniques. So let's take a look to it. Okay, I have launched the script, and it is asking for the type of secret sharing I want to use. So let's say that I want to use n out of n secret sharing. So I select the option 1. Then I can insert a message, for example, the string secret. Then I can insert the number of parties, for example, 4. And here I can see what is going on behind the scene. So the script has decided to represent our secret as an integer number, that is this one, into this group. And then the shares are computed as we have seen during the presentation. So here is share number 1, here is share number 2, and so on. And then after the shares are computed, the script suggests to send S1 to party 1, S2 to party 2, and so on. Then the part S1 to S4, if they want to reconstruct the secret later, they just have to sum their shares modulo Q, and then convert again the integer they obtain to a string, and here it is, secret. Cool. Now we can also take a look to another case of secret sharing. So let's run the script again. For example, let's say we want to use T out of N secret sharing. Again, the message is the string secret. We can insert the number of parties, 4, and the number of parties that is required to reconstruct the secret, let's say 2. And in this case, we can see that the maximal unqualified set are all the set of parties composed only by one party. And again, here we can see the shares and how they have to be distributed, and how the secret can be reconstructed. And that was all. If you want to play with the script, you can find it on GitHub, as I said before. I hope you liked this presentation, and to see you next time.